So yeah, I'm Matteo from the University of Basel and ETH Zurich, and today I'm going to present you our work toward the optical quantum control of helium-3 nuclear spin. So if we are here today, we probably know that atoms are a great system to perform measurements. We can measure time, rotation, forces, electromagnetic field with really high precision. And one of the key parameters that sets like the performances of these devices is the coherence time of the system. And if we look among atoms, which like where are the longest coherence time demonstrated, helium-3 probably is one of the record candidates systems. So the helium-3 is the isotope of helium that has 2 protons and 1 neutron. And because of this imbalance, there is a net spin 1/2 in the nucleus. And it has demonstrated like days-long coherence time, and also is already used in several like practical applications, like in medicine for the imaging of lungs and respiratory system, or also for sensor, for neutron filters in accelerators facilities and so on. But the like kind of limitation that this system has is that the nuclear spin is not directly optically accessible with light. So now the question would be, how do people even polarize, or how do you read out the spin? And like the tool that is often used is the helium atoms themselves. So actually what one can do once the helium atoms are confined in this glass cell is to apply a RF, radio frequency field with 2 electrodes. And this RF field will ignite a discharge inside the cell, because atoms are like brought to a very high energy state that then rapidly decays in a metastable state, this 2,3s1 state. And this rapid cascade process is what give rise to this light that you see from the cell that really fluoresces. And once the atoms are prepared in this metastable state, then there are optically accessible transitions. Here you see a diagram of the hyperfine structure of these 2 levels that I'm considering here, the S and the P levels. The optical transition is at 1083 nanometers, which is quite a convenient wavelength. And among these several optical transitions that we can see here between the S and the P states, there is one that is particularly interesting. And is this C8 transition that highlighted here in blue. And this is interesting because it's a transition between a spin 1/2 manifold in the S state and another spin 1/2 manifold in the P state. And so if you are a bit familiar with like atom-light interaction, you know that if you have a spin 1/2 transition, you don't have these problems of like tensor interaction and these kind of complications that then really give dynamics between light and atoms that is a bit nasty. So for the rest of my talk, I will focus on this C8 transition. And just to go back to the motivation or like to how this transition is used to polarize helium atoms, the idea is that there is a process taking part between metastable atoms and ground state helium atoms that are metastability exchange collision. So what happens is that when you have this discharge inside the cell, a small fraction of ground state helium atoms are brought into this metastable state, and they will collide then with the ground state atoms. And when this collision happens, the electron spin and the nuclear spin exchange between the metastable and the ground state atoms. So what happens is that you can optically assess the metastable atoms, polarize the metastable atom, so because of the hyperfine interaction between the nucleus and the electron gives also a polarization of the nuclear spin. And then through this metastability exchange collision, you transfer the nuclear polarization, the electron polarization to the nucleus of the ground state atoms. So, so far we have seen that the nuclear spin in helium-3 can be optically polarized via metastability exchange optical pumping. It can be read out using resonant light with the same principle, or NMR techniques using like a small coils around the samples and so on. And it has demonstrated this long coherence time. But what about if we want to achieve like quantum noise limited readout of the nuclear spin, or like if we want to spin squeeze, so go to non-classical state preparation to improve like measurement precision. So in order to do this, in this new system, we can take inspiration from what has been done in alkali atoms. And one of the main like tools using alkali atoms is the Faraday interaction to perform like a measurement-based state preparation. So in Faraday interaction, what happens is that you have like a probe laser beam that is detuned with respect to some atomic transition. This probe is linearly polarized, and when it goes through the polarized sample of atoms, there will be like a phase shift in the light polarization that depends on the spin state. So you see here the Hamiltonian between the spin J of the sample and the Stokes parameter S of the light. And this Hamiltonian describes this shift that I mentioned in the polarization that you can read out with a polarization analyzer and therefore perform a measurement of the atomic spin based on the measurement of the light. So if you look what happens in the Bloch sphere, you can start with this polarized state that is like a coherent spin state at the equator of the Bloch sphere. And after the measurement, since you gain information of where the spin is pointing, then the state will result like a squeeze after this quantum non-demolition measurement, and the squeezing will be given by your measurement precision. So how can we now learn from this tool and apply this like a technique to helium, the nuclear spin in helium-3? So this is what we have been doing together with our collaborators in Paris, the group of Alice Sinatra. And what we have been considering is this setup in which there is like a miniaturized cell full of helium-3 that is inside an optical cavity that enhances the interaction between light and the atoms. And then there is a polarization analyzer that looks at the shift or like the rotation in the polarization of the light. So here you see like the level diagram that is like just a selection of the energy states that I showed you before. There is the 3½ and 1½ manifold of the metastable atoms. And you see that the cavity field is addressing the transition between the 1½ manifold in the metastable state and the 1½ manifold in the excited state. We can eliminate the 3½ manifold, and at the end, the main result of our theoretical work was that we can see the combination of the Faraday interaction between the metastable atoms and the light with the dynamics of the metastability exchange collision as an effective Hamiltonian that takes the form of a Faraday Hamiltonian between the light and the nuclear spin. So this metastability exchange collision mediates the interaction and give rise to a Faraday interaction with the nuclear spin that otherwise would be impossible. There is this rescaling factor, small n over n, that basically is the fraction between metastable atom and ground state atoms that rescale the strength of interaction. So we have performed this theoretical analysis. We plug in some like numbers, for example, considering a small cell, a cylinder of 2 centimeter length and 5 millimeter diameter. We have like some number of atoms for a pressure of 2 bar inside the cell and room temperature. A cavity with a finesse that is reasonable of like 50 and like some 5 milliwatt of Faraday probe. And what we get is like a squeezing of around -8 dB that therefore can be useful to perform quantum enhanced measurement. So here we did some simulation, but probably for the sake of time, I will skip these details and we can go back if you ask some question. Apart from this theoretical study, we have been working towards like a experimental implementation of this idea. And first of all, we consider like a setup with this helium cell inside a 4-layer magnetic shield, one of these twin leaf shields that we have seen in the talks before. And we use a pump beam to polarize the ensemble and then the Faraday beam to read out the nuclear spin using like a detune probe with respect to the C8 transition. And here you can see the measurement of the SY and XS nuclear spin components, when we polarize the spin, then we send a small pulse that kicks the spin away from the direction of the magnetic field so that the spin starts precessing around the magnetic field. And we use the Faraday probing to monitor the dynamics, so the classical dynamics of this spin precession around the magnetic field. And then we compare this with some numerical simulations. What we have noticed during these measurements is that depending on the detuning between the light and the C8 transition, there can be also some more complicated dynamics. So here in this spectrum, you see where the Faraday probe usually is. So it's like a couple of gigahertz red detune from the C8 transition. But of course, in these level schemes, there are many, many more transitions that have a larger detuning, of course, but they are present. And what these transitions can lead to are like these tensor interactions that I was mentioning briefly before. This basically is the idea that the Hamiltonian between the atoms and the light is not just simply this so-called Faraday or vector Hamiltonian, but it can be something more complicated that also includes higher order spin components, so like F square terms that are coupled to the light. And so what we have been studying was like a detailed study of how the prefactors between these different parts of the interactions, like the vector, the tensor interaction of the 1/2 and 3/2 manifold, they are combined together when we do a Faraday probing. So in this plot that you see on the bottom left of the slide, you see in different colors the prefactor between the different interaction terms that appear in the Hamiltonian. So the blue would be the one that one wants, that is the pure vector interaction of the Faraday Hamiltonian. And then there is the orange and the green that are the coefficients of the tensor and vector interaction for the manifold, 3/2 manifold of the metastable state. And so also it's interesting to see that there are many possible working points, for example, points where the tensor interaction goes to 0, or points where interactions like have different signs and so on, that probably could be interesting or could be exploited depending on like what it's interesting for the application. So to summarize the results of our research, we have shown that the metastability exchange collision can mediate Faraday interaction between the nuclear spin and light. We propose a concrete scheme to prepare nuclear spin squeezing in helium-3, and we measured a classical spin dynamics of the nuclear spin using Faraday probing. In the future, we would like to go to a quantum noise limited readout of the nuclear spin, to manufacture a small cell inside a good cavity with a nice finesse that allows for an enhancement of the interaction between helium and light, and understand more these tensor interactions that are inevitably there because of the many transitions that are present. So with this, I thank you, and I thank the collaborators and the people that take part in this research. So Philippe Trottner from Basel, my supervisor, and the group of Alice Sinatra, Alain Serafin, and Ivan Castin from Paris.
Thank you very much, Matteo. For the time being, there is no question on the chat. I'm turning to the audience. Are there questions from the audience for Matteo?
What is the rate of metastability exchange, and is there something that you can do to control that? Is that a knob that you can turn in the experiment, or is that something that you're just stuck with based on the...
So the main parameter that set the rate of the collisions is the ratio between how many metastable atoms there are and how many ground state atoms there are. And usually what is easily made is a fraction, one metastable atom out of 1 million of ground state atoms. So now, in terms of rate, it's like, you know, Alice, it's like a couple of megahertz, no?
So for a metastable state, is megahertz rate, the collisions with the ground state.
It's megahertz rate, yeah.
And then for ground state, it will be Hertz rate.
So if I understood the answer, this is the rate at which a given metastable atom would exchange with a ground state atom. And if you wanted to somehow use interactions with the metastables to measure the quantum state of the ensemble of ground state atoms, then, but would you need then 1 million collision times?
Yeah.
A second.
And this is basically what sets this scaling here in the Hamiltonian, this rescaling between the interaction with the...
Can you repeat?
Yeah, so basically the collision rate for the metastable atoms is like 2 megahertz. And there is this rescaling that depends on the fraction between metastable atoms and ground state atoms, which is like 10 to the 6. So this is what basically slows down kind of the interaction between light and the nuclear spin.
Thank you, Matteo. Are there other questions from the audience? Not. If there are some coming, then we will come back afterwards. But thank you very much, Matteo. And we'll going to the second talk for this session, given by Thomas Ruster from Rohde Schwarz. And he will tell us about quantum spectrum analyzers. So, Thomas, the floor is yours.
Yeah, thank you, Jacques, for the kind introduction and for inviting me here to this symposium. It's a really nice place. Yeah, I'm here to talk about our recent project, which is we're trying to do spectrum analysis with atomic vapor cells. Before I dive into the physics, I would like to introduce our company a bit to you. Rohde Schwarz is a privately owned company with around 13,000 employees around the world, from which around 3,000 people are working in our headquarters in Munich. And since you all work in quantum optics labs, you have probably encountered already our test and measurement equipment like spectrum analyzers, network analyzers, frequency generators, and so on. But actually, Rohde Schwarz is doing, and it's developing many more technological systems, and we are also providing solutions for network and cybersecurity. So, for example, if you came here by plane, you might have encountered one of our body scanners at the airport. Yeah, we as a company, we have a strong ambition to stay at the edge of technology and what's possible technically. This is why we are looking into various fields of new technology such as AI, 6G, cloud, but also quantum. And quantum is, this is why I'm here today. This is what I'm presenting today. To give you an example of how technology has evolved over the last years, I want to show you the recent development of spectrum analyzers. So over the last years, especially the analysis bandwidth and the frequency range of our devices, they have increased drastically, not only with the release of entirely new devices, but we are also regularly releasing upgrades and new options for our current devices to stay on top of the technology. And you can be very sure that we are already developing a next generation of devices with even better specs. But this trend comes at a price. We put strong constraints and demands on our components that we use in our spectrum analyzers. For example, especially analog digital converters and FPGAs, mixers, and so on. Especially when considering the large analysis bandwidth that the people need today, it's very important to have very fast components. So you need a very fast analog digital converter to reach a high analysis bandwidth. And we see that this becomes more and more difficult as we approach higher bandwidth. And the question is, are there solutions to this problem by maybe switching to other technologies? And yeah, and quantum technology might be a good candidate for this. So there are various groups working on quantum sensing systems with atoms, with Rydberg atoms, or with NV diamonds. And in principle, we are interested in all of those systems because we see in each system opportunities to improve our current measurement devices. It just happens that in this project that I'm currently working on, we are focusing on atomic vapors. So yeah, let's look a bit into the project that we are doing right now. So we are attempting to do broadband spectrum analysis with atomic vapors. And with broadband, I mean that we want to analyze the spectrum of a large frequency span, as large as possible, but we want to show and analyze it instantaneously without doing a sweep, as we know it in a classical spectrum analyzer. And we tackle this problem by doing a parallel approach. So on the one hand, we are working on a proof of concept setup, but we are also working on simulations at the same time. And this approach, it's very important for us because on the one hand, we need experimental data to verify that the simulation is working correctly and predicting correct results, but we can also use insights of the simulation to improve our experiment and to learn what is really happening in the experiment. Okay, let's start with the project team. We are working closely together with the University of Basel, with Philipp Treutleins group. His postdoc Yongqi, he's here, and he's mainly in charge of the experimental setup, which is located in the lab in Basel. My main job is to develop the simulation, and my colleague Melvin, who's also here, he's mainly doing the project management work. We also get occasional support by other internal departments, by specialists for certain aspects. On this slide, I also want to mention CSEM. CSEM, they deliver the vapor cells that we use in the lab in Basel. This contribution, I think it's a key aspect for us because it's essential if we want to bring this scheme into a product so we can mass produce devices with these vapor cells. Okay, some of you might be familiar with the microwave imaging setup, which is already there in Basel. So in this setup, they're using a thin rubidium vapor cell, which is located in homogeneous magnetic field. And they analyze the transmission of a laser beam in a specially resolved way with a camera. And when they bring an antenna or an RF circuit or something very close to the vapor cell, the camera can image the power distribution of the RF field, which is created by the RF circuit that we want to test. And then the camera can directly show the RF distribution, which is close to the circuit. And this is very interesting on its own. But when we first approached Philipp Treutleins group in Basel, we suggested to do the following scheme for spectrum analysis. And I remember this meeting well. I think we made Philipp very happy when we told him this concept because this is essentially the already existing setup in Basel, but we just have to remove one of the magnets in their setup. And removing one of the magnets, it turns the homogeneous magnetic field into an inhomogeneous one. So we have a spatially dependent resonant frequency in the rubidium atoms along one axis of the cell. And this inhomogeneous magnetic field, it behaves like a Fourier transform. Instead of measuring the spatial power distribution of the microwave field by the camera, we directly measure a frequency spectrum without doing any additional image processing steps. And this concept is very well suited for doing this broadband spectrum analysis, because the camera really, it measures the entire frequency range at once in one picture. Okay, when we started the project with the University of Basel, I visited their lab for some time, and together, I helped Yongqi rebuild the setup for doing the spectrum analysis measurement. And on the right picture on the slide, you can see a close-up of the core of the experimental setup. You see the rubidium gas cell, which is located like above a big magnet. And you see that we moved a PCB coplanar waveguide very close to the cell. So if we apply a radio frequency to this waveguide, the field created by the cell will overlap with the rubidium atoms and will interact with the rubidium atoms in the cell. And luckily, already in the very first week of working together in the lab, we could already measure the first experimental spectra. So here you see two example images where we have applied with a signal generator a multi-carrier signal to the waveguide. And you nicely already see on the left-hand side of this rectangular region of the gas cell, you can see the spectral lines that are created by the microwave field. And on these images, we can also already see the analysis bandwidth, which at this time was around 500 megahertz. Okay, after that, Yongqi kept improving the experimental setup in Basel. He managed to improve the bandwidth to around 1 gigahertz. He worked a lot to improve the optical setup and also replaced the rubidium vapor cell to get a much better signal-to-noise ratio than before. You can see on the picture that the spectral line is much clearer and also much bigger, even when applying the same microwave power. Okay, so much for the experimental setup. Now I want to show a bit the status of the simulation. So, the general principle is this. We simulate the atomic physics of each rubidium atom. That includes like the RF interaction between the rubidium atom and the RF field, but also the laser interaction and also the internal levels of rubidium, of course. And we combine this physics with the calculations for the movement and the collisions of these atoms in a buffer gas cell. And if we carry out this calculation for each pixel of a simulated two-dimensional rubidium cell, we will get simulated camera images in software. And this process is very important because we can verify that we understand the physics of all these processes correctly, because if I program all the formulas into the software and we get a good agreement, we know that we understand the processes. But we can also then use the software to estimate the performance of a future optimized prototype, which is targeted at this application. Okay, going a bit more into detail. In principle, what I have to solve is a master equation for the rubidium atoms that includes an additional diffusion term which takes into account the movement of the atoms. Of course, this is a very complicated equation, but we can solve it in a simplified way, because we are doing a pump RF probe scheme in the experiment. That means, for example, we never turn on the microwave and the laser at the same time, and we can also apply certain simplifications. For example, for the optical pumping process, we solve this equation. We ignore the phase evolution of the atoms, and instead we approach it with a rate equation approach. And we don't solve the RF interaction combined with diffusion, but we solve it in a two-step process. So first, I calculate the Rabi oscillations without diffusion, and then I apply the diffusion process. This is a strong simplification, of course, but it is valid under the assumption that the magnetic field gradient is small enough. Okay, let's compare some images. So here I try to simulate an experimental measurement exactly with the same parameters in the simulation software. And you can already see an excellent qualitative agreement between the two images. There is a slight quantitative difference. The simulation expects that the optical signal is a bit stronger. But we know that this is due to the optical pumping process, which works a bit less efficient in the experiments than what we expect from the simulation. But otherwise, I think it's a very good agreement. Okay, to summarize my talk, we are working very closely together with our partners, and I think with great success, and it was very fun doing this so far. It's important to tackle this approach in parallel by doing experiment and simulation at the same time, and to understand what's going on. And we are currently working on performance estimations for a possible future improved prototype. For example, we are working on simulating the sensitivity, the frequency resolution, and the dynamic range of a future setup. And if this performance estimation, if the numbers are good enough, we want to build a prototype of this scheme in the headquarters in Munich and Rohde Schwarz. Thank you for your attention.
Thank you very much, Thomas. Going to the questions for the time being, as usual, it gets slowly to questions on the chat, but we just get one. What is the tilt in the images? In extent, so the stripe is not perfectly horizontal.
You mean the experimental image here? So I think the reason is, of course, it's possible that the cell is tilted a bit to the magnet, but I think this is a slight inhomogeneity in the magnetic field. So if you look at a broader picture, I think you can see that, now does the cursor work? I will try. That the line will it will have a curve like this probably somewhere.
Okay, we have a second question. How would you evade Tesla class magnets in the anticipated commercial system?
What does await mean?
Evade.
Evade. We wouldn't, because I mean the frequency span that we want to reach, it depends directly of the maximum magnetic field and the magnetic field gradient that we reach. And if we want to go to very high frequencies, we have to go to high magnetic fields. And I think, fields of 1 Tesla and above will be necessary. Okay, thank you.
Are there other questions for the time being on the chat? There is one. But from the audience, are there questions for Thomas? No, so I go back to the chat. You mentioned that the homogeneity in the magnetic field is important. Do you know quantitatively how this affects the system? What is the homogeneity you need?
Yeah, honestly, I don't think that the homogeneity is too important. If the field is not perfectly homogeneous, it will lead to a tilt or curves in those lines. But I mean, to analyze the spectrum of the signal, it's not entirely necessary that the field is perfectly homogeneous or linear. I think we can work even with curved lines if we do some kind of image processing at the end of a measurement. But yeah, I think we can work with some inhomogeneity in the magnetic field.
So with that, are there questions in the audience? Seems not to be the case. Thank you very much, Thomas.